Okay, today we'll be talking about generalized impedance converters, or GICs. They also take the name sometimes when you employ them as simulated inductors, gyrators, or simulated capacitors, or frequency-dependent resistors components. So it will look something like this. It will look something like you apply a voltage right here, and then you got an impedance that you have simulated, and then you got, and it's grounded. And then let's recall from Laplace that the impedance of an inductor is equal to j omega L. Impedance of a capacitor is 1 over j omega Z. This is the basic structure of GIC. Basically, impedance can be modulated by Z1 times Z3 times Z5 or Z2 times Z4. So what are GICs and what can you do with them? Okay, so let's answer to that. Well, you can simulate inductors. Correct. You can simulate capacitors. And frequency-dependent resistors, or just frequency-dependent components in general. And why would you want to do that? Well, you know that in integrated form it's very tough to make inductors, so being able to make them with a few op-amps and a few other passive components it's very nice. And you can create them to a very, very accurate value. Same with capacitors. A capacitor of more than a few hundred picos is very hard to simulate in integrated form. So it gives us a nice way to make them. And then op-amps, which are what the circuit uses, they are very easy to manufacture in integrated form, so it's very nice. Okay, so next question is, so how can you actually accomplish this? So how can you accomplish this? So mathematically, to simulate capacitors, what you would do would be you make either of these values, either Z1 or Z3 or Z5, a capacitor, so capacitor, and the other, everything else resistors, or you make or Z2 or Z4 an inductor. Okay, so what about to simulate inductors? So you will make C2 or Z4 a cap, or Z1, Z3 or Z5 an inductor. So why does it turn out to be like that? Okay, so that's the question. The question is why. Well, let's take a quick example here. So you make Z1, Z3, Z5 and Z4, just resistors. Okay, and make Z2 a capacitor. So what will you have? Okay, so therefore you'll have Z equal to Z1, Z3, Z5 over Z2 times Z4. This is just the the equation that we had before. And now we replace with the components we just chose. So R1, R3, R5 over R4 times the impedance of capacitor 2, 1 over AC2. Rearranging that a little bit is going to give us R1 times R3 times R5 over R4. And this one comes up, it's 2. Now we substitute for S, J omega, and therefore we'll get that. So therefore Z is equal to J omega times R1 times R3 times R5 times C2 over R4. Okay, so that is an inductor. It's a simulated inductor, a simulated grounded inductor. Why? Well, we said before, remember the impedance of an inductor is equal to J omega L, correct? This part right here takes the form of L. And so in other words, L, this is the expression that they give you in the book. L is equal to R1 times R3 times R5 times C2 over R4. Okay, so it's very nice. So yeah, we realize how to actually simulate an inductor, but we want to know what's really going on in the circuit, correct? Alright, so for that, so let's see, but what's really going on in the circuit? So that's the question we want to answer. So for that, we'll do 2 thought experiments. So we will do 2 thought experiments. As we said, thought experiments. So one of them is going to involve AC analysis, and the other one is going to be DC analysis. In more simple manner, AC analysis is just taking and sweeping that frequency and see how the circuit actually responds to it. DC analysis is just applying a step. As soon as you flip the switch, what happens to the circuit? So now there is a few things that we should recall. One of them, how does the inductor react at different frequencies? So now at high frequencies, it acts as an open. So omega going to infinity will mean that that's an open. At low frequencies, it acts as a short. Omega going to 0 means that it will act as a short. So now that's for an inductor. What about for a capacitor? Since we have a capacitor in the circuit, we have to see how it reacts to changes in frequency. So at high frequency, it acts as a short. Okay. At low frequencies, it acts as an open, which means that we're going to have something look like this. Okay, so we'll also be using ideal op-amp analysis to kind of understand the circuit, so let's recall what that means. say we got an op-amp right here, positive terminal, negative terminal, then we get the output. One of the things that you should remember, this is VP, this is VN, is that for ideal op-amps, VP is equal to VN. The op-amp will try to do anything to keep the difference between these two terminals to 0, right, to keep them equal. And then the other thing that you should remember is that looking into the op-amp, the impedance is going to be infinity. So there is basically no current going into the positive terminal or the negative terminal. Now, the impedance looking at the output of the op-amp, so RO, is going to go to 0. In other words, the op-amp can source, ideally, any current to keep the voltage as needed. Okay, so that's nice. Now, we want to, as we say, we want to see what happens to the circuit as we increase the frequency. Okay, so let's just write that really quick. So C2 capacitor will start acting as a short. So that means that we can replace it in the circuit. So I'm going to erase it out of there and put a wire. Okay, so a few things to note. Op-amp 2 is going to try to make its positive terminal equal to its negative terminal. How can it do that? Well, one way it could do that is by increasing the voltage at node 2. Once it does that, you're going to see there's going to be a drop at this point, which is going to make V negative equal to V positive equal to VA. So you're going to have VA right here. Since these two nodes are at the same potential, there's no current going through R1, correct? So the first thing is there's no current going through R1. So there is no current going through R1. So where is the current that's coming from R3? Well, it's going into the low impedance pad of op-amp 1 right here through this wire right here. And then op-amp 1 is going to try to make its negative terminal equal to its positive terminal. And then once it does that, then you're going to end up with VA, Vin equal to the negative terminal op-amp 2, which is equal to the negative terminal op-amp 1, which is mirrored into the positive terminal of op-amp 1. So therefore you end up with VA down here through R5. Okay, so let's rewrite that really quick. So op-amp 2 will put a higher voltage at node 2, so that's that guy right there, so that VP equal to VN equal to VA. Now the current through R3 will be sunk into op-amp 1 through this low impedance pad. Therefore what we have, if we were to put an ammeter right here, so a little ammeter in series into A, what we have will be that at omega going to infinity, this element will look something like this. Get some C, where the current is going to be equal to 0 because there's no drop across here, since both of them are equal to VA. And then the V looking into A, the voltage drop from this structure, it's going to be VL equal to VA. So at high frequencies, the circuit behaves as an inductor, which is what we wanted. Now looking at the circuit at low frequencies. So at low frequencies, C2 now, so that's not cool. C2 now is an open. So let's get that guy out of there. Alright. Okay. So let's start with the first thing. Since the input impedance of op-amps is very large, then you're not going to have any current flowing through the negative terminal of op-amp 1, neither through the negative terminal of op-amp 2. What that means is that there can't be any current going to R3, right, since C2 is an open. Since there is no current going to R3, and we know that op-amp 1 is going to try to make its negative terminal equal to its positive terminal, there can't be any current going through R4 as well. So let's write that. Okay. Since the input impedance of op-amps is very high, therefore IR3 has to be equal to 0, and since VP1 is equal to VN1, then IR3 is equal to IR4, which is equal to 0. But you have to note something else. Then where would the current that will be going through R5 be coming from? Well, R5, it's virtually in series with R4, right? There's no current through R4, so there can't be any current through R5. So R5 is also equal to 0. What that means is that there is no current through R5, no current through R4, no current through R3, so there can't be any drop across any of those resistors. That means that the ground is going to be pulled up all the way up until this node, the node that is common to the negative terminal of op-amp 1 and negative terminal of op-amp 2. Op-amp 2 will further try to make its positive terminal equal to its negative terminal, which will put ground at node A. The last thing is that since the op-amp 1 output impedance is very low, then we're going to have basically a maximum current going through R1. And we're going to have node 1 driven to a negative voltage. Because remember, this is A is ground. So the only way you can get current going through it is if it's the output pin of op-amp 1 is negative. So let's write that out. So VP2 equal to VN2 equal to VA, which is equal to 0. Further, op-amp 1 will put node 1 at a negative potential and will sink current into its low impedance output pin. So what does that mean? Okay, so let's redraw that component that we talked about. Just see grounded. So at high frequencies, so as omega increases to infinity, the current, it's gonna increase, or it's gonna become max, right? And the voltage VL is equal to VA, which is equal to just ground, so equal to 0 volts. So this is also consistent with an inductor at high frequencies. With an inductor, with an inductor at low frequencies. Yeah, that didn't make any sense. An inductor at low frequencies. An inductor at low frequencies, the current is just going to be a wire, correct? So the current is going to be max, and there's not going to be any drop across its terminals. Okay, so now let's go on to the DC response of the circuit. So DC response. That is what will happen as we put a step into the circuit. So what we really want, all we're doing here is we are hypothetically thinking about what's going to happen as you take a step and put it into a grounded inductor. And we're going to do that at three different cases. We're going to do that at t equal to 0 minus, t equal to 0 as soon as you close that switch, and at t equal to 0 plus, a long time after you have closed the switch. Let's also remember that in this case, if we were to have a real inductor, well, the behavior you expect would be the inductor will resist the change in current but voltage will change instantly. So now let's look at what happens at t0 minus. 0 minus, so this is just like having an inductor just floating, correct? That's all you're going to have. So in reality there's not going to be any charge stored in this capacitor. What that means is simply that VA is equal to VC2 to the upper plate, VC2 the lower plate, equal to VP2 equal to VN2 equal to VP1 equal to Vn1 equal to 0 volts. Correct? I mean, we're still following the ideal op-amp. It still follows, but doesn't really give us much intuition. Now, the next one is a little bit more interesting. So here is the story about what happens. This is the transient response. In other words, at t equal to 0, right? As soon as you flip that switch. So op-amp 2 will raise the voltage at its output in order to keep its negative terminal equal to its positive terminal. What that will mean is that there will be some current flowing through R3. That current will go on to charge the lower plate of the cap, which will push some current out of the upper plate of the cap, which will go on to cancel out the current coming down through R1, and the remaining will go on through the low impedance path of op-amp 1. So let's write that. I feel like sometimes it's easier, if sometimes for people to understand. We'll raise its voltage. So raise its voltage at VO2, that's that node right there. To make, so make Vn2 equal to Vp2 equal to Va. Remember, to make the two inverting and non-inverting terminals equal. This will push some current through R3, correct, charging C2 lower plate. Yes, but remember the voltage of the capacitor can change instantly, so it pulls a current out of there to keep the voltage the same. And then C2 upper plate will pulse basically what's happening is just making IR1 equal to 0, correct? Because you got current coming here from the pulse of the capacitor, the current coming down here from VA, and then you got some coming here. So the currents will cancel out, giving a current of 0. The other thing is, so op-amp 2 is going to make a voltage higher at node 2. It's going to drop onto some voltage which is going to be equal to VA by op-amp 2. The two terminals are going to be equal. Same thing is going to happen here. It's going to drop through R4, make the terminals of op-amp 1 equal, right? So in reality, op-amp 1 is going to make its positive terminal equal to its negative terminal. Op-amp 2 is going to make its negative terminal equal to its positive terminal, which is equal to VA. So in other words, VA is going to come down all the way down here, and it's going to drop through R5. I mean, virtually, correct? So let's summarize what we just found. Basically what we have is same component right here, which is going to have the IL is equal to 0 and that VL is equal to VA. Correct. So that's right for an inductor. As soon as you close that switch, it's going to resist the change in current. So IL is going to be equal to 0, and but the voltage drop can change instantly. So we're going to see it right there. Alright, so now let's take a look at what happens after a long time after you have closed the switch. So we know that the input impedance of op-amps is very large. So basically there's no current going into the input terminals. So again, and then the capacitor after a long time is charged up. Right? So there can't be any current going through R3. Yeah, if there is no current going through R3, there is no voltage drop across R3, which means that in order for op-amp 1 to keep its terminals the same, there can't be any voltage drop across R4, which means there is no current as well, right? So now that follows that op-amp 1 has its negative terminal equal to its positive terminal. But if there is no current going through R4, then R4 is in series with R5, and the positive terminal is not sourcing any current. So therefore IR4 is equal to IR5, which is equal to 0. Which means that there is no voltage drop through R5, no voltage drop through R4, and no voltage drop through R3. I mean the ground is going to move up all the way from this node, all the way up high to this node, right? To the negative terminal common to op-amp 1 and op-amp 2. So we know that ground is now at the negative terminal, but now op-amp 2 is going to try to make its positive terminal equals to its negative terminal, which means that we're going to have ground at the input to the circuit, right? You're going to have ground all the way up there. So let's write what we just found, correct? So the capacitor is equal to 0, and which also make now at steady state the capacitor upper plate will be negatively charged, which means that the node A is at 0 volts, the upper plate is negatively charged, so there is no current flowing through R1. Further, it goes through the output pin of op-amp 1, which is very low impedance. So basically you have a very large current, which is only contained or only determined by R1, by the resistance, correct? So let's write that. Steady state, the capacitor upper plate would be negatively charged, thus creating a drop through R1. And a low impedance path through OA1 will sink most of this current. Correct? So this is analogous, just to put it in perspective. This is analogous to the following circuit. So you got a resistor right there, resistor right here, voltage divider at this node, and you get an inductor right here. So in the beginning you have that the inductor will oppose the changing current, but after a long time the current through the inductor is basically going to be maximum, right? So it's going to just act as a wire, right? So it's going to bring this node right here down to 0 volts. And that's exactly what we see after a long time. So let's redraw this really quick, just to conclude. So then again, IL is max, and VL is equal to 0 volts. So thus we explain how the circuit actually works, just doing a simple experiment of AC analysis, DC analysis, and we figured out that the circuit actually behaves as a grounded inductor. I actually used this simulated inductor for a graphic equalizers to design bandpass filters for every stage, and it works pretty nice. The only recommendation is to get a dual package or a quad package so that those op-amps are very, very well matched. So that's it for simulated generalized impedance converters. So hope you enjoy it.